very exciting speaker. He's going to talk to us. This is Neil Kermode, and he's going to talk to us about hydrogen generation and also using the ever-abundant energy around our seas and how we can capture some of this energy and how we can actually use it to generate hydrogen. And so it's very interesting. It's an area where, you know, I think that there's great opportunity, especially in the UK being an island. And then after Neil's talk, we then will go to the AGM and we'll have to do the normal process of going through all the things that has to be done at the end of the year. But yes, so I'll stop talking and I will allow Neil now to start presenting to us and giving us some very useful and interesting information.
Thanks, Josh, indeed, Alex. I appreciate that. Could I just double check, what time are you going to the AGM? Just make sure I don't dribble on.
1 hour, so
that's fine.
At 1900. So
oh,
yeah.
That's fine. Excellent, good.
If it's really exciting, you can go on a little bit because the AGM we can go through relatively quickly.
Okay, well, the advantage of Zoom is you can always tell by the numbers when they drop off, so that's a big thing. So good evening, everybody, and I hope you're now seeing the presentation. Excellent, good. So good evening, everybody. So my name is Neil Kermode. I'm the Managing Director of EMEC, which is the European Marine Energy Centre. We're based at 59 degrees north up here in Stromness in Orkney. Ironically, I actually come from Bournemouth, and that's and Margaret and I have met through a couple of bits and pieces involved with the Society of Bournemouth, but also with you guys as well. So anyway, I feel slightly displaced being all the way up here, but I have to say it's been absolutely beautiful today, and I'm glad the weather's got out of the way. What I want to do today is talk to you, as Alex said, about three things really. Why we're doing what we're doing, which really starts from our marine energy background, and then I want to go on after talking about marine energy to talk about hydrogen and how we're using it, and indeed some of the things that we are seeing coming along the track, because I think our view might be slightly ahead of some of the policy issues that are around at the moment. So I hope you'll find it interesting, and as I said, happy to take questions at the end. So why are we actually bothering with all this lot? Well, I'm old enough, having been born in 1959, to remember the fuel crises we've had in the past, where frankly we ran out of fuel when OPEC decided to put the prices up, and we ended up on 3-day weeks and goodness knows what. And this really sets several things in motion in government, which emerged really looking at the diagrams on the right-hand side of some diagrams produced by the Department of Trade and Industry of the day, which showed where there was energy in the sea in the form of wave energy and tidal energy, wave at the bottom, tidal at the top. And in addition, there was also work done which produced a report, which was for the Office of Science and Technology, a foresight report in 2000, which basically also mentioned that there was energy in the sea, and this could be extracted if only we knew how to do it. And so that then gave rise to some work that was undertaken by Highlands and Isles Enterprise, who are the local development agency up here in the north of Scotland. And that realised that if we were going to be able to harvest energy, then the best thing to do was have a test centre where the first devices could be put into the water. So the resource itself we've got in the UK is pretty special. We've got something like half of Europe's tidal resource and over a third of Europe's wave energy resource. And if you look at the lower one, in the case of wave energy, you'll see there's energy hitting the north of Scotland and also the southwestern approaches. There's no energy really hitting the middle bit because Ireland acts like a large breakwater. And however, it does mean that Ireland itself has also got a huge amount of energy. So in these islands as a whole, we've probably got around 50% of Europe's wave energy as well. So the point is, what can we actually do with that? And it was realised that the energy we could see from the seas could actually power about a fifth of our present electrical demand. And if we get to use this stuff, it gives us huge opportunities. It gives us opportunity in the form of industrial innovation, security supply, which when we started back in 2003-4 wasn't that important, but obviously has become disturbingly more important as a result of Ukraine and the other crises kicking off, and also these energy sources are basically carbon free, so they give us a chance to reduce our carbon emissions. The reason Orkney was picked for holding a test centre was really a combination of several things. We have big waves and strong tides. The area there, you can see the tides running between the little island and the larger island in the background. The larger island is called Edie and the little one's Muckle Green Hole. That little gap between those two, 500 million tonnes of seawater an hour go through that gap. And so by putting machines in those tides, it was thought we could extract energy. In fact, I'll show you how we've been able to do that. We're also very close to big harbours, and that photograph is taken in 1919, I think, which was with the German fleet interned in Orkney, and in the foreground is a flying boat station. But we actually had two navies actually situated in the harbour here, and that means we've got the space in which we can assemble the equipment that's needed to go out and then do marine energy. We're the most northerly point on the national grid, and I'll talk more about that in a moment, with presently the most northerly point, which means that energy we generate, or electricity we generate, can flow into the national grid and do really useful work. And the other thing we've also got here in abundance is we've got people who've got experience in a variety of marine trades and businesses, so diving, construction, fabrication, boat operating, but also we're well versed in using energy, because one of the things that's happened here is we have had the Flotter oil terminal here for coming up on 50 years, and so there's been a variety of people who've been trained in a lot of energy related activities. So it was decided that to make the most of marine energy, we needed to find a way to do that, and the best thing to do was start a tidal test centre. And so we were built as a test centre. We have something like 36 to now nearly 39 million pounds of public funding has gone into us, and we're a not-for-profit organisation testing, and we test machines independently. So we are an independent test laboratory, and we have this vision of being a pioneer in low carbon, in a new low carbon future, and we try and do that across marine energy and now increasingly into green hydrogen. And the point is we're trying to get those to play their part in the international energy system. As an innovation catalyst, our job is to try and grow these new technologies and do it in such a way that is quick, so we reduce the time, we do it inexpensively, and we do it with a minimum risk, so it's safe. We try and do all these things together in a marine environment, which actually, A, is beautiful, but B, is pretty challenging, frankly. So what have we got by the way of facilities? Two types of site, wave and tidal, are fundamentally different. And so the wave site on the left-hand side is situated on the west coast of Orkney, looking out into the North Atlantic, where the waves come crashing into the cliffs, having left Canada, or been built up between us and Canada. And on the right-hand side, the Fall of Warness, that little body of water I showed you earlier. And in both cases, we've got cables that run out into the sea. And those cables are connected to the substations, and the substations have got switchgear within them. And then there's an instrumentation at sea, which is measuring the way in which the waves move or the tides move. On the wave side, giving you an example of the extreme nature of the energy we have here, we've measured 18-metre high waves on our site, and the Fall of Warness moves at about 4 metres a second, which is about 500 times stronger than a diver can actually hang on to something. So these are extreme conditions we're in. So what have we done with this over time? We've had these sites, and we've had something like 35 different devices, well, exactly 35 different devices. They tend to come in integers, from 11 different countries and 21 different developers. And so there's a variety of some of the machines we've seen on site, which have been looking to try and harvest energy from the sea. And I'm going to talk to you about some of the most successful ones in just a second. But the journey we have to take developers on is one which is important for all innovation, and it's really about how do you install these machines? Do they survive? Are they reliable? Can you maintain them, and will they work in an energy system? Are they operable? And if you know the answer to all of those, and you know the costs for all of those, you can get to a point where you can decide whether what you're trying to do is cost effective. And this process applies really to all technologies, not just marine energy. How do you make this stuff work in the system in which you're trying to insert it? And these lessons are often have to be learnt really much in this order, because you can't You'll never know if it survives if you couldn't install it, and you'll never know if you can maintain it if you're unable to, if it never survived a storm. It's these sorts of things you have to find out. And the point is, once you know the answer to those things, then you stand a chance of finding a place in the market. So what have we actually been doing so far? Well, as I said, there's 35 different devices been in place, but what's actually in the water at the moment is the machine at the bottom. That's by a company called Motion, and they've got their machine initially on our scale test site in the sort of fairly placid waters of Scapa Flow, which is where that photograph was taken. I say placid, we get 4-meter high waves even in there. And then the machine on the top right-hand corner is from a company called AWS Energy, and that machine has done its tests and is currently sitting in a local yard, and they're looking to see if they can reinstall it and do further tests on it. Both of these are wave machines. In addition to that, we've also got machines that are out on site. I've got the word now in inverted commas because the machines are actually in for maintenance at the moment, but they are due to go back out again imminently. And the top, the one on the left is for a company called Orbital Marine Power, so I'm going to talk about more in a second. And they're a Scottish company, and this machine sits on the water surface, and then you can see there are a pair of arms, one of which has got O2 written on it, and those arms are then lowered below the machine, and then those red rotors are then engaged in the tide, as you can see in the bottom photograph. And we also have another company called Magellanes, who have the ATIR machine, which is built in Vigo and towed up and has then been installed on the site. And they're both seeking to generate between 1.5 and 2 megawatts of energy from the tides as they come and they go. So a little bit more in detail about the orbital machine, because this one is directly relevant to what we're seeking to try and do and show why this is important, because that's the diagram of the machine in a schematic form. And you see the arms lowered. Those blades are 10 meters long each. And so about 1,200 tons of water a second pass through those rotor planes on each rotor. So these are having to deal with serious forces. So they are strong and they are carefully built. This one was actually built in Dundee, and this is the machine before it had the ends welded on. So a lot of the equipment was installed, you see, on skids, on containers, and then forklifted into the body of the machine. And then the machine itself has got a series of compartments where the kit sits. But the important thing I really want to drive home in this is that these machines are actually built at Texo in Dundee, and they had the nacelles added on, so that the gearboxes were added on, and they came from in part from the Germany or Austria, I think, I can't remember, maybe Poland. The blades came from the Solent, and then the whole machine was finally assembled. And between them, they had something like 147 different companies from the supply chain supplying into this. And the point is, this is done from equipment from all over the UK. And it had around about 80% UK content in this machine. And what this is about, as I said at the start, is how do we harvest this energy and how can we create useful economic activity? Because these are real jobs. These are real people actually doing proper welding and proper hydraulics and electrical skills and glass fiber and all the 1,001 different skills that are needed to make this stuff work. And that's what's going into the machine. But in addition to that, there's also the jobs, the people who will then go and install this equipment, those skills, which I said we've got in abundance in Orkney. In addition to that, you then find you need infrastructure to make this stuff work. And this is a pier extension that was built for some tidal turbines. And we also find people are investing in the vessels that are needed to actually go and install this stuff. And these are multi-cats, each of which is between £3 and £6 million, bought by local companies to actually go and install these machines. And the point is, by setting off this journey of making this stuff work, we've ended up with a lot of people actually getting proper jobs in this. And just a little bit from a civil engineering point of view, I'm really keen on infrastructure, because once you've got infrastructure, stuff happens. And the case in point is here, which is this pier, which I think you see my cursor, which is moving along the pier extension that was built onto the ferry terminal. And on the day this photograph was taken, there were 4 tidal turbines being worked on. Point is, no infrastructure, nobody gets to work on this stuff. So lesson there, you need to make this real. And part of our job here at EMEC, the reason I'm talking to you is to make this real in several senses, because if we can make it real to people and they can realise that this is an industry which is about to happen, we should find our way through the various policy challenges. And that's why we had people like Anne-Marie Trevelyan up with Richard Graham MP when she was the Energy Minister, showing her the orbital machine actually on site doing its thing. And then we had the pleasure of the Duke and Duchess of Cambridge, as they were at the time, up onto the machine, showing them the realities of this. So that's what we'll be doing from the marine side of things. The point is, how does this lead you to hydrogen? Well, it's what we have is a really interesting catch-22 situation, which is that we can't prove this kit until we've got the grid. In other words, we need the grid to prove our kit, but you can't have the grid until you've proved your kit. In other words, nobody will bring you a wire to export this energy unless you can definitely know you're going to use the grid. So this gave us a real problem, because what we had done is we'd installed installed EMEC in Orkney, in a place that had a little bit of grid capacity available, but didn't have a huge amount more. So we've actually used up what's going on, what's available. So what does that mean? It leads us to some interesting challenges. I'm going to talk more about those and how they played out. But the point is, the grid is not the only energy source we use. And as a community, we're quite energy literate. We know what's going on in the area, because people are experiencing the strong winds and the strong tides and the waves and the rest of it. And people here have been quite sensitized to energy for quite some time. So an energy audit was done back in 2014, and it was repeated in 2019. And that energy audit explained how we use energy in our society in Orkney. And for those with context, I should have said, Orkney's about 22,000 people. We're spread across, I think it's 17 islands are inhabited, but most of the people are in the main town of Kirkwall, which is about 9,000 people. And then about 3,000 in the town which I'm in, which is Stromness, and the rest of us are scattered across the isles. But this graph, this Sankey diagram, shows how the energy we use. And the point is, you see kerosene at the top of the big sort of purpley arrow, and then below that electricity. And then we've got in the road transport area, road diesel is big for us. And then further down, you get down to the blue bit of gas oil, which is big for marine transport. And those are used in a variety of ways, but the bottom line is we basically use the top bit for heat and light, and the bottom bit is largely transport. And so as a community, we've been working really hard on putting in renewables to decarbonise our electricity supply. And we've been pretty successful. We've now got to a point where we've produced more electricity than we've needed every year from renewables since 2013. And so we're now in a position where something like 130% of our electrical demand comes from renewables. So the point is, we've done electricity, and we're using some of the electricity to put a dent in some of our diesel and petrol addiction in the form of electric cars, which have been taken up with alacrity here. But the point is, we haven't really touched the rest. And the point is, all the effort we've put in so far, we've only done about a fifth of the decarbonising of our energy system, let alone our production system that's got to go on. So there's still a lot to do. And that led us to the next point, which was, so if we know we are in a position where the grid is full and we need to prove more technology, how do we get the energy out of the sea, and what do we do with it at that point? Because if the grid is full, that's not really an option. We know we can do other things with the fuel because we have a need for energy, as we showed by this Sankey diagram. So how can we break out of the corner we're in? And that's really where we started to look at hydrogen for storage. And so we started looking, first of all, about the tidal output and could we do something with the tides? Now, this graph shows a 4 megawatt cutoff. And basically, I had a 4 megawatt grid connection on the Isle of Ely, as I pointed out earlier. And so that was the limit of how much tidal energy I was allowed to put into the grid. But actually, we thought, well, what happens if you do put more in? Or you install more generating kit? Let's say we put an extra couple of turbines on, we can generate 6 megawatts. Could we do something with the red bit? I.e., we're not allowed to put it into the grid, but could we electrolyse water, store the hydrogen, and then turn the hydrogen back into electricity in the gaps in the tides? And that would effectively give us a resultant output of a constant output from renewables. Now, obviously, that's something of a silver bullet because one of the challenges with renewables is intermittency. Often predictable intermittency, but nonetheless it's intermittent signal. So that was where we started from. And we started a project which looked to do that. I'll talk more about that in a second. But in effect, we were going to take the hydrogen and turn it back into electricity. But we had some further work done, which looked at the value of hydrogen once we'd started this off. And we quickly noted, because we're quite quick on graphs, is that if you take the electricity and turn it back to, so to take the hydrogen and turn it back to electricity, the hydrogen was only worth about 30 pence per kilogram. Whereas if you used it to propel things, in our case ferries, it was worth about £4.60 a kilogram. So it's worth 15 times as much if you used it to move something than it was if you just turned it back to electricity. So very quickly we realised that our plan in the top right-hand corner might not be the best thing to do with hydrogen. We might want to modify that. And so we looked to do something different, because the ferries themselves do use a huge amount of energy. In this case, that one ferry used around 16 megawatt hours of diesel a day. So could we do something else? So we did a series of projects, one of which was called Surf and Turf, which actually brought a wind turbine and a tidal turbine together and tried to use the energy for that in a means by which we were powering ships. So this is a photograph taken at the launch of some of the work we were doing, and it shows several bits. We produced the hydrogen through electrolysis up on the Isle of Ely. We put it into these trailers and drove these trailers down. Those trailers were then parked in the compound on the left-hand side, and we either stored them flat or we left them on the trailer, generally left them on the trailer. The hydrogen was then passed to a fuel cell, and the fuel cell comprised 3 25 kilowatt units, so 75 kilowatts of fuel cell. And that fuel cell was then used to power the ferry in the background when it tied up alongside at night. In addition to the electricity we were producing, we also produced heat, and that's why we actually sent the heat to the adjacent building to demonstrate basically combined heat and power. And so the idea was whether we could power the ferry when it tied up alongside at night. Now, we actually wanted to put the hydrogen onto the ferry. I'll talk more about that in a second, but that proved to be a challenge for regulatory purposes. But the other thing we also did was look to put hydrogen into vehicles. But the main thing we got out of this were the people to actually make this stuff work. And so by starting a project off, we drew in several bits in terms of training, in terms of the logistics, in terms of the vehicles, the practicalities of technology in the marine environment. And all these things together started to build a little bit of a hydrogen ecosystem. And you can see, you may be able to see, depending on what device you're looking at, but there's a graphic on the side of the trailer on the right-hand side, which shows the Isle of Ely in the top, and then the port at the bottom showing the idea. And this is a very much a public relations exercise, an informative process to show people what was going on. And we had to work our way through the challenges that people would naturally bring up about using hydrogen in an urban environment. So all these things were catalyzed or brought to life by actually doing a real project. Looking at the ship in the background, that was one of the ships we actually looked to use hydrogen on, not just in terms of electricity, but actually as a propulsion fuel. And so the MV Shappensea, as it's known, is effectively sort of a landing craft type of ferry. It runs to the Isle of Shappensea, which is about a 30-minute trip north from Kirkwall, the main town, to the adjacent island of Shappensea. And work was done when it was in the annual refit, which involved putting in a variety of vents in the side of it, and modifying the engine to put an element on top of the air intake, which would allow hydrogen to be injected into the air intake of one of the auxiliary engines, one of the diesel engines. And then cylinders were put in below deck. It's just a mock-up of one of the cylinders just to prove we could get it in through the hatch. And then the bottom right-hand corner is the kit actually installed without the casings on the outside of the hydrogen store. Now, in fact, we have found it impossible to get this vessel to actually operate. And the reason for that really has been from a regulatory point of view, because the Maritime Coast Guard Agency have got a series of processes that they run through in order to make sure that shipping stays safe. And it proved to be impossible to get our way entirely through those processes and get permission to put hydrogen into the engines, even though that's done on trucks on a routine basis. It's done in the automotive space. It proved impossible to get that through the MCA. So that project was extended quite a while, and then subsequently stalled. We are looking to seek to have another go at finishing that project off, but we'll wait and see whether we can actually fight our way through the regulatory thickets to get to the end of that. So at the moment, there isn't any hydrogen shipping going on right at the moment, I'm afraid to say, in Orkney. The other thing we've also done was working with a company called ZeroAvia, and we're doing projects, or two projects with them principally. The first one was a hydrogen-powered aircraft, which in effect was a 6-seater aircraft that had its fossil fuel engine replaced with an electric motor, and it then had hydrogen aboard with fuel cells, and it then made the electricity to run the engine whilst it was flying. And that did a variety of pieces of work, and the project was looking to do a 300-mile flight. Now, in fact, the project didn't actually conclude with that, and they moved on to some work with a different aircraft at the bottom, which is a Dornier, which has been converted to take hydrogen. And once again, they've changed one of the two engines to run that on hydrogen. To do that, it required the production of hydrogen down near the airfield, and also the means to boost the pressure of it and then be able to refuel aircraft. So a refueler was built, which has road certification, and that's been the first road certified hydrogen refueler that's been used in the UK. But in addition to that, we were also approached by Rolls-Royce to supply them with hydrogen to put through a gas turbine, which they did at Boscombe Down, which gave them some interesting and useful results. But one thing that really had a big effect on us at EMEC was when we met the crowd through a company called IGTL, particularly a guy called Pete Oswald, who had done some work to come up with a fuel synthesis process, which took using some of our electrolytic hydrogen, combining that with carbon monoxide, and that actually was then used by the RAF. That produced gasoline, and that gasoline was then supplied to the RAF, who used it in their first ever fully synthetically fueled flight, and has ended up in the Guinness Book of Records. And to be honest, this was quite a moment for us, because suddenly we saw that whilst some of the experimentation we'd be doing with gaseous hydrogen was interesting and was taking us in various directions, and we were seeing various technical challenges, those technical challenges rather dropped away if you turned the stuff into synthetic fuel. Because if you turn it into synthetic fuel, you keep doing what you're doing at the moment. In other words, it comes in a jerry can rather than an awful lot of drama having to handle either hydrogen as a gas, or worse still as a liquid, which we've decided we're not going to do under any circumstances. And so we have really started to pivot our thinking towards the potential for the production of synthetic fuels. And I'll talk more about that in a few minutes. So what has all this lot done? So we've ended up with building up quite a lot of hydrogen knowledge, some about the production, which has been challenging, storage and transport, as I said, with the means by which we move the gas around, and indeed the skill transition. What skills already exist, and they do exist, frankly, in the oil and gas industry, but need some tuning. How do we get those skills together? And then finally, the means by which you actually supply this gas and put it into various other uses. Excuse me, I'll take a slip of coffee because I'm getting a bit dry. So, where are we actually making the gas? What does it actually look like? Well, we have our site up on the Isle of Ely, and we expanded that site. Originally, we started off with our cables coming in from the sea and our substation and our connection to the grid. But we then expanded the site when we started to work on hydrogen by putting in the electrolyzer and the hydrogen storage. But we've also recently added, a year or so ago, the building over on the left-hand side, which is a flow battery, which is our energy storage site. Because if we return, I mentioned the community turbine, sorry about that. If we return to the original idea of of electrolyzing hydrogen and then turning it into electricity and getting a resultant electrical output, we realized that in fact what we now need to do, given the demand we're seeing for hydrogen, is actually optimize hydrogen production rather than obsess about a standard flat electrical output. And so we've taken the intermittent tides, we are storing energy from the extra tidal turbine, storing that in a flow cell battery, and we're then discharging that to electrolyzer and then giving us a resultant continuous hydrogen output, or that's where we're working to at the moment. We're just in the process of doing some final commissioning on some of the battery. And the point is here, and it's a really telling point, I think, for everybody, is that innovation is a journey of discovery. We started off trying to do one thing, and have ended up doing something really completely different. You know, we started with tidal energy, and now our focus is very, very clearly shifted towards or building on that to then start to do work about hydrogen, and our views about how hydrogen should be used has dramatically changed. So, interesting experimentation as far as it goes, but if it just stays as a sort of a 0.5 megawatt electrolyzer, which is what we've got around, or 670 kilowatt electrolyzer, yeah, that's not really going to put a dent in the hundreds of gigawatts of energy that the UK is going to need to work. And we're really pleased to say that during the time we've been working on the hydrogen side of things, we have encountered a change in mood in some of the oil and gas industry, and particularly one of the organisations we're working with has been Repsol Sinopec, who are an oil company who own the oil terminal, which is in Scapa Flow. And just for context, that black and white photograph I showed you with the flying boat station in the foreground and the ships in the background, right in the background of that, in the haze, would have been this island. But there wouldn't have been an oil terminal on it back in 1919. But the oil terminal is there. It was built, say, 50 years ago, and it's the area within a dotted line in the middle. And Repsol Sinopec have announced with various other partners that they are intending to convert this to a hydrogen production facility. And in part, we think that's due to the work that's been going on, that we've piloted certain activities and shown the way on certain things. And they're looking at a variety of things, whether it'll be hydrogen or indeed other fuels. Because it's really important to realise, if you think back to that Sankey diagram, that we don't just use electricity. We do use other fuels, and we can either displace some of our existing fossil uses with hydrogen directly. We'll talk about that as well in a second. We might actually just end up using hydrogen as a bit of a vector, because there's a huge change coming to the generation mix in the country. In the top right hand corner, those boxes and the various triangles and parallelograms and stuff are areas that have been leased as part of the ScotWind leasing round for offshore wind. Now, at the moment, the UK is using about 45 gigawatts. I didn't check before I came on tonight. No, that figure in the bottom left-hand corner is from a slide from a while ago. It's probably in the summer. I reckon we're probably using high 40 gigawatts of electricity at the moment. And the proposals for ScotWind are going to bring around 25 gigawatts of electricity to the network. So we're getting close to 50% of what the UK is using in the way of electricity at the moment. And the graphic in the middle shows the additional green blocks, which are the areas which are probably going to get developed in due course. They're just schematic shapes at the moment. But those areas are likely to get developed for offshore wind. So we could be talking about another 100 gigawatts of offshore wind coming from the north of Scotland. And that somehow we've got to get it from the top of the country to the bottom. And the graphic on the left-hand side is the existing national grid. And those bits of sea, and indeed Orkney, are not even on the transmission system. So if we are going to try and move the energy from the top of the country to the bottom, are we going to move it as electricity, or might we choose to move it in a different way? And the conclusion we're coming to is that, in fact, we might want to move it as either a gas, or we might even want to move it as a liquid. And if you move it as a liquid hydrocarbon, not liquid hydrogen itself, but as a liquid hydrocarbon, you can actually do effective bulk transfer of energy from one end of the country to the other. So the point is, I wouldn't say the jury's out at the moment. The jury is wandering towards the courthouse and hasn't been impaneled yet. What we need to do is do an awful lot of work to make the cases, to explain how energy could be shifted, because I do think the contemporary narrative of us just building more and more wires might not be the solution we finally end up with. So the last little bit really was about where I think we're going, the future piece. And I'm now going to take you off on a small chemistry lesson, if you'll bear with me for a second, which really is about, you think about how the country operates at the moment. And you may recall that Sankey diagram where I showed there was gas oil, there was jet fuel, there was kerosene, and gas oil, and a variety of bits and pieces. And the point is, they're all frankly the same stuff. They're all fundamentally diesel, and they're diesel in very slightly different forms. So we do things using diesel at the moment. So what are we going to do when we don't have diesel? Well, I would argue we're in trouble. So I think there are some things where we're going to have to use diesel. But what we can do now, showing this using that fuel synthesis process I showed earlier, is we can actually make diesel. So I'm now going to try and convince you as to why this is a good idea. So if we look at a graph which is produced by DMV, first of all, we plot against the gravimetric density and the volumetric energy density, i.e. megajoules per litre vertically and megajoules per kilogram horizontally. I'm sorry, my scales have got a bit compressed there, I'll sort those out. But basically what it comes down to is diesel is there. And then if you draw quadrants around that, you, based on weight and space, what you find is that you end up with stuff that's the bottom left requires more space and is heavier than diesel. Above that, it requires less space and is heavier than diesel. You can read for yourselves. However, if you then take all the other fuels that we use at the moment and plot those on the graph, and the orange dots are liquid fuels, the green dots are hydrogen based, the red is natural gas down the bottom end, and then solid on the left-hand side, you can see that there's quite an interesting cluster, but basically there's nothing to the top and the right above diesel. So there's nothing that requires less space or is lighter than diesel. The other thing that's quite disturbing is if the gases, generally speaking, don't stay where they are on their own. They need to be contained. And the containment is actually quite complex. And that containment adds weight. And if you look at the containment for things like liquid hydrogen or compressed hydrogen to 700 bar, the weight of the cylinders, the weight of the insulation, the weight of the infrastructure to hold this adds a huge amount to them. And so basically, a lot of these materials shift very quickly down to the bottom left-hand corner. So the bottom line is there is nothing above and to the right of diesel, i.e. nothing better in terms of weight and density. And frankly, including storage, there's practically nothing half as good. Now, that then gives us some real challenges, because if we are going to continue to do things, we've got some choices. So if we think particularly about planes, which are probably the most weight and space constrained forms of transport we use, if you're going to use this, you've got a choice. You can either use the same fuel and keep the plane and infrastructure, or you keep using diesel. Or we can change for a worse fuel, as shown by the previous graph, and don't go so far, i.e. we have to stop and keep refueling every now and then, or carry less, i.e. we take less load or less passengers or less whatever it is, or we change the plane and the infrastructure, or finally we don't fly. And the point is that I think to answer the last question, are we going to choose not to fly? And I would say we just did that experiment, big style, during COVID. We all stopped flying, no planes were in the air, and we then said, are we going to do this again? And we rushed back to it with great joy. So I don't think it's likely we're going to not fly. We can do various things that reduce the amount of flying, but we are going to fly. If we are going to fly, how are we going to get the diesel? Now the question is, are we going to get the diesel by drilling holes in the ground and then doing carbon abatement, things like promising to plant trees, or are we actually going to make the synthetic fuel? Because there is a choice of how we do this. Because if we start at the top, we have carbon in the atmosphere. We can capture it out of the atmosphere. We have the technology to do it. If we then synthesize fuel with it, we can then store that in buffers and tanks and stores, burn the fuel, and the carbon ends up back in the atmosphere where it started from. So we haven't added to the carbon budget. Now, we've still got SOx and NOx and particulates and bits and pieces, so I'm not saying it's without impact, but the point is that it is a way to actually do this, but it does require direct air capture of carbon. And if we can capture that carbon in the form of the carbon dioxide, or better still carbon monoxide, but probably had to be carbon dioxide initially before we process it, we stand a chance of being able to do something, because as I said before, only about 1/5 of the job's done, and how are we going to do most of the rest of it? So I think that's a solution for some of the work we're looking at, particularly the aviation side of things, because frankly, aviation is really hard. And based on what we've seen, hydrogen is going to be a challenge. It is not going to work for all of the things we're trying to do. But we also know that since 2019, we've seen an awful lot of work go on in the electrification process, and batteries have got so much better. So what do we think the energy mix is going to look like in 2030? So in 2030, we're pretty confident that in fact, everything is going to be in electricity at some stage. Everything. So we will be using renewables in various forms and producing electricity. And that electricity, some of it will be supplied pretty much to point of use. So a certain amount of domestic stuff is going to be electric, but very much most of the light transport, and indeed quite a lot of the heavy transport on the planet, is actually going to be electrified. In terms of our heat, we're likely to then satisfy that really from heat pumps. That's going to be the principal technology that works. I've had a heat pump for years. I don't know what the fuss is about. So heat pumps will be a big part of making this all work. And then I think the other thing we're going to do is a large amount of electrolysis, which will produce either synthetic hydrocarbons or synthetic ammonia. And then there'll be something sorting out the rest of it. But basically, it'll be a mix of all the stuff above. And that's where I think we are going to be going in 2030. Now, the question is, will it be a large amount of ammonia and a little bit of synthetic hydrocarbons, or will it be a lot of hydrocarbons, or indeed, will it become an export? Because certainly from our point of view, we could end up with gigawatts, so thousands of megawatts of energy incident around these islands, which we can turn into other things. So we think synthetic hydrocarbons may well become a significant export opportunity for these islands. So finally, what's really the energy transition going to be about? As far as we're concerned, the deal is electrify everything you can now. So cars, trains, buses, bicycles, motorbikes, whatever it is. If you can electrify it, because it's much more efficient than producing synthetic fuels, but you have to electrify it. The energy transition is more than just electricity. The energy transition is much more than electricity, and we are going to need liquid fuels. But the point is, we're not going to need fossil liquid fuels. Provided we can get the carbon out of the atmosphere, we can have liquid fuels that do not involve fossils. And the point is that pioneering work is underway, but goodness knows it's so slow. And we have to urgently pick up the speed and the pace to make this all work. So overall, from EMEC's point of view, we've been really concentrating on doing this whole learning by doing piece and creating that pre-commercial knowledge, by having practical demonstrations of things and trying to make those really work. Because together, we've been battling away with things, and we think we've actually been making progress towards net zero on air, land, sea and air. But there's so much more to do. So the final thing I want to do is close with an appeal, which is really based around the fact that we need ideas. We need people with ideas. We need people to bring forward concepts. We need people to really roll their sleeves up and get on with this. And if I tie back to a quote we have on the wall in the office above the door as you come into EMEC, it's a quote by JFK. And he said, "The problems of the world cannot possibly be solved by the cynics and critics whose horizons are limited by obvious realities." We need people who can dream of things that never were and ask why not. That's what we do. I'll be really happy to take any questions. Thanks for your time.